Hello, everyone. Welcome. I'm Joachim West, product manager at LAYTEC. And in this talk, I want to inform you or present you a little bit about in-situ and ex-situ metrology for VCSEL production. To start, just short for LAYTEC, who we are. We are a metrology company founded in 1999 in Berlin as a spin-off of the technological university here. We have around 70 employees now and operation worldwide ongoing. And so far we have sold over 2,500 systems. Our business is process integrated optical metrology for the markets, primarily semiconductor and thin film industry and academia. That includes the applications of lighting, laser, photovoltaics, and glass coating, and many more. So to just give you an introduction of what we do in various industries and markets, we do metrology for LED production. We also provide in-situ metrology for laser production, thin films for functional glass, as well as power devices and also photovoltaics. Our products are ranging from in-situ products that are directly mounted on a deposition chamber, such as ALD, atomic layer deposition, sputtering, PECVD or MOCVD, and others. We also provide inline solutions for conveyors, roll-to-roll, and then also ex-situ tools like for ex-situ mapping of wafers. To do all that, we have various material databases to make it possible that we can do the analysis in our software that we also provide with our tools, and to be able to do the simulation, analysis, fit functions, and integration into the chambers and reactors that we are working on. So let me go briefly to a manufacturing chain of a semiconductor. In this example for a laser, we always start with the substrates at the beginning. They are loaded into a deposition chamber where we come into play with our in-situ metrology. And at that point already, during the growth run here, our metrology can already predict in some extent the device performance at the end at the packaged device. After this epitaxial growth, we can also have the ex-situ tool for get more in-depth spatial uniformity information about the wafers that we grow. And we can also provide inline metrology for like front-end front-end conveyor and back-end conveyor packaging stuff. So go a bit more in detail into the in-situ metrology in semiconductor industry. What you see here is an MOCVD system that we are typically working on. First of all, we start with loading the wafers on a susceptor, and the layer stack that we want to grow is provided by the software of the MOCVD system. Our tool sits on top of the reactor and measures then the in-situ data. So here's an example of the in-situ data that we measure, and you can use this data then for process controlling, for monitoring, for statistical process control, and such. The measurement provides then as information wafer and pocket temperature, layer thicknesses, growth rates, wafer curvature, ternary composition, and surface morphology, and many more. You can use all of this information then to have the best outcome for your semiconductor device, e.g. in a laser. A little bit more in depth, this is a fingerprint of a DBR growth that you can monitor with our APTT VCSEL. What you see here is the y-axis in time, the x-axis in wavelength, and the color, the reflectivity is coded in a color. The more red it is, the higher the reflectivity. And what you can do then with our tool is you can put out transients at specific wavelength if you go in the vertical direction, and you can also derive a specific time or a specific spectrum at a specific time that you are interested in. So the benefits for this spectral in-situ metrology for a VCSEL grower is you get the growth rate, you get surface roughness information, you get information about the composition, interface grading, and especially the cavity position and the stop band position that you're most interested in for the VCSELs. How does the Ex-situ metrology look? It's like in this box, we provide white light reflectance and photoluminescence. Here you see the inside of this box with the measurement and a loaded wafer. So we can load wafers from 2" to 200 millimeters so far. And as a result, you will get the spatial reflectance information or photoluminescence information, and you gain the information about uniformity of your wafer, for example, VCSELs. For the VCSEL analysis, we provide stop band position, stop band width, cavity information, cavity dip information, such as position, depth, width, and also the more classical information, growth rate, layer thickness, and ternary composition. The EPICS is the mapping tool that I was talking about. This is looks a bit more detailed like this. It has a combined measurement head inside that combines the PL measurement with reflectance measurement. You can map your wafer in an XY mode. And the combination of this measurement head, the PL combination with the white light reflectance, makes it possible so that you don't have to realign and change measurement heads when you go to one or the other. Wafer sizes up to 200 millimeters are possible to measure. And we can customize your spectral detection range regarding wavelength and resolution from roughly 200 to 2000 nanometers. We can provide up to 4 photoluminescence excitation lasers, typically visible and near infrared, and also include advanced analysis features. So to sum it up, you get the full story in 3 dimensions for if you combine epicurve TT VCSEL and the EPICS to understand your wafer in 3 dimensions. That means you get a timely information and a transient or the spectroscopic information with our in-situ measurement tool, the epicurve TT VCSEL. And together with the EPICS Ex-situ, you also gain a lot more knowledge about your spatial uniformity. So that's it for now. Thank you for your attention. And if you're interested, let's get connected. You find the information of us here, like our LinkedIn link and the website, and also our email address. I will be also in the booth for the next half hour, I think. So if there's any questions, just come to us. And yeah, thanks for your attention again, and see you later. Thank you very much.